Welcome everyone to the Otago Energy Research Centre seminar series. So today we've got Boyang. He's a research fellow at the Department of Physics, and he's going to talk to us about some work he's doing with Richard Blakey on producing hydrogen from solar. So,
yeah. Thank you, Michael, and good afternoon, everyone. Welcome to my talk. So the work I'm going to present today is built upon the collaboration between us, the sub-wavelength optics group in the physics department, and led by Professor Richard Blakey, and also the nanophotonics group led by Professor Min Qiu from Westlake University, China. So yeah, so as you can see from the topic, and today I'm going to talk about a technical platform that can improve hydrogen production. So we'll start, So the first question would be, why hydrogen? So hydrogen has been viewed as the one of the future energy source to replace fossil fuel because it's very clean. So the burning product of hydrogen is only water, so there's no carbon emission at all. So which will help us cope with the global warming or this kind of issue. And also hydrogen has very high energy density, by weight, of course, yeah. And also hydrogen is a very important industrial feedstock to produce methanol or ammonia or something like this. So in this talk, I'm going to introduce you that how we plan to use our expertise in nanophotonics to improve the hydrogen production. So I will start with how to produce hydrogen. So currently, the primary method to produce hydrogen is the steam forming of natural gas or oil reforming or partial oxidation of coal. So as you can see that basically all of these methods are based on fossil fuel. So a much more cleaner method is the electrolysis of water. So in this case, we place two electrodes into a water bath, and then we get electricity on. Then the water molecules can be split into hydrogen gas and oxygen gas, and we collect the hydrogen gas from one electrode and the oxygen gas from another electrode. So this method is very clean, but also it's very inefficient and very expensive. So as a result, only 5% of hydrogen is produced using this method globally. So some people, then to solve this problem, some people just propose that we can use a solar cell to generate electricity to drive the water splitting reaction so that we can store the solar energy. Then someone else also proposed that why don't we just directly put the solar cell into a bath, into this system. So that is the photoelectrochemical, the PEC system. And we can see that in the PEC system, the solar cell or the semiconductor is directly placed into a water bath, and the generated electricity drives the water molecules to be split to the hydrogen gas and oxygen gas, so which is known as the photocatalytic water splitting. So for a PEC system, it is very important, very critical to find the right materials to construct the photoelectrodes. So basically, there are two kinds of materials. The first one is oxide-related compounds like titanium dioxide, Fe2O3 and BiBO4, these kind of materials. So if you look at these materials, actually these materials look very transparent, means they have very low light absorption. And also these materials, actually, they are not metal, they are more like a dielectric, means the conduction means the conductivity is very low. So it means that they have very low, very poor charge separation ability. So another kind of material is 3,5 semiconductors, like gallium arsenide, gallium phosphide, and gallium, these kind of materials. So they have relatively high light absorption and relatively high charge separation ability. But the problem is they are very expensive, and also the lifetime, the durability is very, very bad. So as a result, the solar to hydrogen conversion efficiency, the STH efficiency for the oxide-related compounds is very low. It's less than 1%. Actually, usually it's just 0.1%, 0.2% or something like this. And then for the 3,5 semiconductors, so if we only use the material itself, so without any tandem configuration or something like that, so the STH efficiency can be 3 to 4 So it's much higher than the first one, and then the oxide-related compounds for the lifetimes is only hours. For example, 20 hours, 10 hours, or something like that, which means that we need to use the new material systems to develop the PEC system. So next, I'm going to introduce you the new system, the new material we are going to use for PEC. So that is 2D semiconductors. So 2D semiconductors is a member of the 2D materials family. So the first member of 2D materials is graphene. So graphene has won the 2009 Nobel Prize in Physics, and we can see that a monolayer of carbon atoms has been spread into 2 dimensions, which is why it is called 2D materials. And specifically, the 2D semiconductors we are going to use for the PEC systems is the 2D transition metal dicoupling, the TMDC materials. And we can see that the monolayer of TMDC, actually, they are composed of 3 layers of atoms, and the middle layer, this one, is the transition metal atom layers, and which is sandwiched between 2 coupling atom layers, the yellow one here. So the thickness of these 2D TMDC is very thin. It's about 0.6 nanometers. So 1 nanometer is 1 billionth of a meter. I'll give you a reference. So usually a red blood cell has a diameter of 6 to 8 microns, and which means the thickness of the 2D TMDC is only 1/10,000th of the diameter of a red blood cell. So it is extremely thin. So if we use these 2D semiconductors for the PEC system, actually it has a lot of advantages. The first, it has the maximized reaction area. Actually, even if we use the bulk materials, the bulk semiconductors, the reaction, the photocatalytic water splitting reaction area is the same as the 2D, almost the same as the 2D materials, because the water molecules cannot penetrate in depth into the semiconductors. So, and also the reaction can only happen at the surface. So the reaction area is very, very big. And also, it has the solar band light absorption, basically ranging from visible to near infrared. So that is the solar band absorption, these materials. And also the raw materials to produce these 2D semiconductors, they have earth abundant reserves. And also these materials, they don't have the electrics raining from the third direction, which means they have very high charge separation ability. And also, actually they have very good photocatalytic durability. For years, I don't know, but for months, I'm pretty sure there were experiments to prove that these materials can do these experiments for months. And of course, it has its own shortcoming, and that is low light absorption. Actually, for 1 monolayer of the 2D TMDC, the absorption is 10%. It's already very high at such a thin thickness, but the problem is it's too thin. So in this case, when we shine some beam of light shines on the structure, it passes the monolayer once, so 10% of light can be absorbed. So how can we enhance light absorption? So one method is to place a mirror at the bottom. So in this case, the light gets reflected and passing the sample twice, then maybe 20% light can be absorbed. So we know that if we want to enhance the light absorption, then we have to create multiple reflections within the monolayers. And so we can try to make the photons stay in the monolayers as long as possible so that we can enhance the light absorption. But the thing is, how can we do that? Can we add another mirror on the top? Yeah, the answer is no. Otherwise, we would stop the light from entering the systems, of course. So in this case, our expertise, nanophotonics, can play a role. So in nanophotonics, we build very small structures, nanometer scale structures to manipulate or to control the light flow. So specifically for this structure, for these kind of materials, we put a nanosphere or nanometer scale like metallic nanoparticles on the top, so that we can create multiple reflections between the nanoparticle and the mirror, and also we can let the light in the system. So in the next, I'm going to specifically talk about this topic. So I'll start with the nanoparticles. So the simplest form for nanoparticle would be a nanosphere. Here's a gold nanosphere. It has a diameter let's say, less than 100 nanometers. So when a beam of light shines on the nanosphere, then the conduction band electrons inside the nanosphere would collectively oscillate with the external field here, so which is known as the excitation of localized surface plasma. And as a result, which means the incident light is localized or absorbed by this nanoparticle. So as a result, here is the absorption spectrum of the nanoparticle, and we can see at the frequency, at the wavelength of 530 nanometers, actually there's a peak. Means this part of light, the green light actually here, is the green light is absorbed by these nanoparticles. And also by changing the physical geometry of the nanoparticles, actually we can modify the optical properties. For example, here we expand the length of the nanosphere along one dimensions, then we can have the nanorod. And we can see that the absorption spectrum actually redshift with the growing length. Another way to modify the optical properties is to break the symmetry of the dielectric environment. For example, we can introduce a gold film or gold mirror at the bottom of the nanosphere. And in this case, the symmetry of the dielectric environment along the Z direction, along the Z axis, is broken here. And in this case, when a beam of light shines on here, and then the the incident light can be highly concentrated and resonating at the gap between the nanoparticle and the gold film. And here we can see, here's a scattering, but actually it's absorption spectrum. Here we can see the absorption spectrum. Here's a resonance here. So when we change the distance between the nanoparticle and the gold mirror, when we change the gap spacing, actually, for example, from 3 to 7 nanometers, we can see the blue shift of the resonance here. So this structure actually is a very popular structure in nanophotonics, and because it has very good light absorption ability, it can concentrate light, it can concentrate incident light between the nanoparticle and the mirror. And so we have lots of applications. A great deal of efforts have been paid to study these kind of structures, including our own work. So in the next, I'm going to introduce you some of our work to study this kind of structure. So the first one, you can see that we place some gold nanorods on the gold mirror here. And so here it is the simulated electromagnetic field distribution. We can see that when the gap spacing is very small, it's only 1.5 nanometers, the incident light is electromagnetic field, so it's light. So the incident light is highly concentrated at the gap between the nanorod and the mirror here. But when the gap spacing is 20 nanometers, we can see the field, they have the same scale, and the field is much weaker than the 1.5 nanometer case. So, which means the smaller the gap spacing, actually, the stronger the field is concentrated at the gap. And from the scattering image, we can also see that is a scattering image from single particles. From the scattering image, we can also see at the gap spacing of 20 nanometers, the scattering image is very bright. But at the 1.5 nanometers, actually, it's very weak, which means the incident light is absorbed at this case, so that the scattering image can be darker than this one. Yeah, and also about this structure. Here, before it was a single nanoparticles on the gold mirror, and we can also fabricate an array of nanoparticles on the mirror here. And here is the SEM image, the scanning electron microscope image. You can see here's the structure. And in the spectrum, we can see here's the experiment, and here's the simulation, and we found that at certain frequencies, even 100% of light can be absorbed by these structures. 100%. Of course, that's certain frequencies, and the frequencies depends on the shape of the structures and also the gap spacing between the nanoparticles and the mirror. So then we have already known that these kind of gap resonators, they are very good light absorber. But then we have to ask, where did the absorbed light energy go? So here I'm going to show you one experiment. So here, in this experiment, we shine a laser beam onto the structure and gradually increasing the laser power. And when the laser power achieves some value, I forgot the value, but it doesn't matter. So we can see the shape of nanoparticle inside the illumination area has been reshaped, has been modified, significantly modified. And we take a closer look. So here's the area without illumination, and here's the area after illumination. You can see that the shape is completely modified, and which means that the absorbed laser power, the absorbed light energy has been absorbed by the nanoparticles and then converted to heat and then melting the nanoparticles. It's a gold, actually, it has very high melting point, but in this case, actually, we can highly concentrated light energy and convert it to heat and then melting the nanoparticle. And next, I'm going to show you, when we shine laser into the structure, actually, we can even make gold crystals here using a high power of laser. Here I'll show, it's the same experiment. We use a different laser power to shine on the structures, and we can see, finally, we can have the gold crystal. Here is a very grainy surface, you can see. So, which means, anyway, now we have already known these kind of structure, the gap resonators, they are very good light absorbers. So what we are trying to do is, we are trying to integrate this light absorber with the 2D semiconductors and try to enhance the light absorption in the 2D semiconductors. And then finally, we want to have very good hydrogen production efficiency. So here's our plan. So we embed or we integrate the 2D semiconductors. So we want to make it sandwiched between the nanoparticle arrays and the gold mirror. So and then we use these structures to construct the photoelectrodes in the PEC experiment. Here is the sample. So we plan to try to enhance the hydrogen production efficiency. And our target is the STH efficiency larger than 15%. According to some literature, actually, that is the commercial criteria for this PEC system. So we have already made some progress. So here, that is our recent progress. So here, in this case, we place some dimolecules. Here's not 2D semiconductors. We place some dimolecules between the nanocube and a mirror here. So here, that is the resonance of the single nanocube on the gold field. You can see it's just a gap resonator. It has the resonance here. Here's experiment and simulation. And then we found out when we place the dimolecules between the nanoparticle and the field, then the single peak actually is split into two peaks here. We have two peaks when we put the dimolecules here. So that is a very clear indication of strong coupling between the photons inside the cavity and the material resonance. So here I pause to discuss the strong coupling here. So for strong coupling, it is a very important concept in physics, especially in optics and light-matter interaction. So in this case, we place some atoms or molecules into a cavity. A cavity, basically, that is the two mirrors photons can bounce between, like in this case. So in this process, the atoms or molecules can exchange energy with photons. So if the energy exchange rate is fast enough, and even higher than the whole system dissipation, then we call it a strong light-matter interaction. And as a result, the electronic levels of the atoms or molecules can be split into two levels. And the splitting here is known as vacuum rapid splitting, and to characterize the coupling strength between the photons and the atoms or molecules. So it is a very important effect, and 2012 Nobel Prize actually has been awarded to a quantum system based on this effect. And also it has lots of applications in our departments. It's quantum information processing and single atom lasing, actually they're all based on these effects. Anyway, back to our structure. We have observed this strong coupling here. Means the photons and atoms, they exchange energy. So, which means that the light not only has entered into the material system, but also it has very fast energy exchange with the incident light. Actually means we are very successful at the point that we introduce the light into the embedded dimolecules. So based on these results, now we are working on integrating the 2D semiconductors with the single nanoparticles here, this one. Now this time we don't use nanocube, we use nanocrystal because we want to change the frequency to match the frequency of the 2D semiconductors. But anyway, we can also see this splitting here. And the splitting in this case is very large. It's over 200 milli-electron volts, and that is the largest rapid splitting at the moment in similar systems. So now this paper is being reviewed by PIL, the topest journal in physics. So we want to build upon these results then to develop our photoelectrodes based on the integration of the 2D semiconductors and the nano gap resonators, and then use it as a photoelectrode in the PEC system and try to enhance the hydrogen production efficiency. So in summary, I've introduced the PEC systems to produce hydrogen, and also I've introduced the 2D semiconductors for the PEC system, and we also introduced our plan using the nanophotonic platform to enhance the hydrogen production. So that's it. Thank you.
I'd like to thank Boyang for his talk. So I guess just a bit of background. Boyang left, and well, we had a gap in the seminar speaking slot, and Boyang graciously filled that slot for us. But we had a very interesting talk. So any questions? So,
given that you're effectively, if you use high laser power, melting your nano part from gold, does that mean that you get some exchange of gold into your 2D semiconductor? Like, is there any mixing with that 2D?
No, that, I mean, for this 2D semiconductor, in this case, we don't use laser to shine on it, and also we don't use high power laser, just a normal, I mean, the laser, I mean, the white light. So it's
so you're not hot enough.
I don't.
No, okay.
Yeah.
yeah.
So related to that, your laser work clearly showed a thermalization of the energy.
Yes.
And for the hydrogen reaction, do you see a thermalization driving the energy input to the molecules, or do you see a more of a traditional absorption?
I think it's traditional absorption. Yeah. At the moment, at least we don't find any temperature increase in our baths or something in our experiment. We don't find that. And for the, I mean, for the melting, sorry. I mean, yeah, for this one, actually, we use very high power laser in this case, and also we focus the laser, so it's different. And if we ran the PEC experiment, we just use a normal, and it's not coherent with light source, so there's no this kind of effect. And we try to see this. We just want to show how good the light absorber is, and also I can give you a reference. So here we put the nanoparticles on the gold mirror so that we can have this effect. If we don't use the gold mirror, we don't use the structure, actually, we have to use 100 times higher power laser to get the same effect.
So, but again, I'm trying to get at that concentration effect. Is it going to be a photocatalytic or a photothermal?
Photocatalytic. Both. I think it's both. But not at the moment, we cannot separate that. I don't know.
Because I think you'd be at a greater advantage if it was photothermal, because then you're going to have a broad band of energy that can fit in rather than needing a specific overlap.
Yeah, that's correct. Yes.
Taking a narrow slice of the spectrum in that. Interesting.
Yeah, the structures that you're looking at, how big are they likely to be? How long are they likely to last?
I mean this. Yeah. Okay. Actually, for the photothermal effects, this area, it is very small. It's just 100 micron or something like this. Yep. But for our goal here, we can make centimeter scale. So we actually I prepared something here. Actually, in our lab, Richard Blakey's lab, we have optical lithography techniques so that we can fabricate very large area of this nanoparticle sample. It's a centimeter.
And how long are they likely to last? What's their life expectancy and such?
You mean this kind of structures?
Yes.
We don't know, years, I guess. It's gold and silver, something. They are very durable. The silver might be not so durable, but for gold, it's
So I guess there's also lots of interest in photocatalytic reactions more generally, right? Not just for solar, not just for solar capture, but just catalyzing reactions with. Does your method have applications in that area as well? Is that something that you?
I don't know.
Okay.
On that one, actually, we are at the moment we design. I mean, we have to use numerical software to design the structures and optics side. So we are doing the structures and fabricate this, and we'll set the samples to color and innovation to do the EC. So for that part, actually, not the expert.
Yeah, certainly there'll be a lot of use in battery technology and things like that. Where you've got those type of similar reactions and increasing efficiency.
Further questions? If not, then we'll
with the scale to like making photo cell more efficient. Would there be another side way that this could go apart from not making hydrogen but just making more electricity?
Yes, actually, that is another target. Yeah. Yes. It's basically the same thing. Yeah.
So do I understand correctly that because you're absorbing the light so well, it could be a way of making better solar water heaters?
Yes. Actually, I think the year before last year there was a Nature Photonics paper. Actually, they use these structures and then they how do they call that? Anyway, to centrify and anyway to make very pure water. Actually, by evaporating the water.
Yeah. Okay.
Same thing. But then in their case, they can prepare the structure using aluminum, so it's very cheap. Yeah. So here we use gold; it's very expensive. Yeah.
So actually creating the nanostructures, how are you doing that? With vibration or?
Yeah, it's the optical lithography and evaporation of gold, of metal.
Very interesting.
How much do you have to refine, do you think, the separations between your nanoparticles on the gold surface?
The separation between.
Yeah, I mean, this is a balancing it between absorbing the light and actually doing catalysis.
Yes, usually it's in centimeter. It's 1 to 2 centimeter, depends on the specific materials. Materials has a resonance, then we have to change the gap spacing. And then in centimeters, then we have to use ALD or other evaporation techniques, something.
Okay, so we'll thank Boyang again and